Hello everyone. We are now going to begin our lecture on the third section of chapter 2 on set theory. Now this particular section is on Venn diagrams and set operations. Now Venn diagrams are a graphical way of describing the relationship between two or more sets. So using Venn diagrams, we can easily tell if two sets are exactly the same, if they are equal sets, or if there are some elements in the two sets which are common and the others are not, or if there aren't any elements common in two or more sets. So it's a quick way of determining from Venn diagrams the relationship between the two sets, and it also helps us perform some set related operations, right? So let's go into more details of that. Now these are the topics that we are going to cover in this section. We are going to begin by understanding the construction of a Venn diagram with two sets. Venn diagrams can be created for more than two sets. In the next section, we will learn about Venn diagrams on three sets, but in this section, we'll start with Venn diagrams with two sets. Then we will have to determine the complement of a set. For that, we have to understand what the word complement means in regards to set theory. So, and then once we understand that, we should be able to determine what the complement of a set is, and then determine the intersection and union. So these are also two important words used in relation to set theory. So we will understand what they mean exactly, understand the meaning of and or. So these two italicized words and or are also two words related with reference to sets. So we will go through that, understand the relationship between the cardinals of A intersection B, A union B. The symbol here stands for union. So A union B, then N of A, N of B, and N intersection B. So we will talk about these symbols and what they mean, how to interpret them, and finally determine the difference and Cartesian product of two sets. So difference and Cartesian products, these are two operations that are often performed on sets. So as we said before, a Venn diagram is a graphical representation of two or more sets which help us to determine how the sets relate to each other. So here it says a Venn diagram is a useful technique for illustrating set relationships, and it's a technique of using circles to represent sets. So we will see that as we go on. But a little bit about the history of Venn diagrams. It's named after the author of Venn diagrams. His name was John Venn, and he is the one who invented it and used them to illustrate ideas in his text on symbolic logic. All right. So this is a little bit about the background of Venn diagrams and what it means. Now a Venn diagram usually starts with a rectangle, and that rectangle represents the universal set U. So you will see pictures of Venn diagrams with a rectangular figure, and inside the rectangular figure there can be circles, and those circles represent the sets created from a universal set of values. All right, so the rectangle represents all values in the universal set, and then we can have different sets, more than two sets, shown as circles within the rectangle. All right, so let's go through the other information in this slide. It says here the items inside the rectangle may be divided into subsets of U and are represented by circles. All right, so again, the rectangle contains all the elements in the universe that we are studying, that we are talking about, or that we are concerned with. And then these circles inside the rectangle represent subsets created from the universe of values. Right? So here we have a picture they've given us. The circle labeled A represents set A, and A will contain elements from the universal set. Again, you can have more than one circle, more than one subset created from the universe of values. All right? Now, the first relationship that we will talk about between sets is called disjoint sets. Now, disjoint sets are sets which have no common elements between them. All right, so let's see what comes up here. It says two sets which have no elements in common are said to be disjoint. So here we have a picture of two circles within a rectangle box. Recall that the rectangle box represents all elements in the universal set, and the circles are subsets created from the set of universal values, right? Universal elements. Now, here we see that these two circles are separated. They are not linked in any way. They are not connected. So, which tells us that they have no elements common between them. All right? And when that happens, when there are no common elements between two subsets, they are known as disjoint sets. All right? And the intersection of disjoint sets is the empty set. Intersection means the common elements. The common elements between two or more sets represent the intersection. It's known as the intersection of sets. Since there are no common elements in disjoint sets, the intersection will be represented as an empty set, just a pair of brackets with nothing between the brackets. All right, and then finally it says here there are no elements in common since there's no overlapping area between the two circles. So if there were any common elements between the two sets, then they would be represented as, there would be an overlap between the two sets. They would be represented something like this. Since there are no common elements, they are completely separated. All right? There is space between them. They are not overlapping in any way. Now we will go into how to present proper subset in Venn diagram. But before that, recall that if set A is a proper subset of set B, then all the elements in set A should be a part of the elements of set B. All right. Now, however, set A has to be smaller than set B. Set B has to be the larger set, and set A has to be the smaller subset of set B. But all the elements in set A should be contained in set B. All right, that's what a proper subset means. So let's see how we represent that in Venn diagram form. So here it says first, if set A is a proper subset of set B, then A is a proper subset denoted by this symbol. All right, there's no line beneath the U over here, the right opened U. And that tells us that it's a proper subset. All right, and then let's pull up all the information in here. So we have here the rectangle, the universal set, and then we have two circles within it. Now circle B is the bigger circle and A is the smaller one, and you see that A is completely inside B. That means all the elements in A are the part of B. Right? That makes it a proper subset. So the representation, the graphical representation in the form of Venn diagrams should look like two concentric circles. The smaller circle is the proper subset of the larger circle that encompasses it. All right, so circle A is completely inside circle B. In that case, A is a proper subset of B in Venn diagram representation. Now we learn how to represent equal sets in Venn diagrams. Now recall that equal sets have exactly the same number of elements and exactly the same elements. Whatever set A has, B has the same elements and the same number of elements. In that case, we say that A is equal to B. So over here it says if set A contains exactly the same elements as set B, then A is equal to B. So both sets in that case are drawn as one circle. So we have our universe represented as a rectangle. Just a second, let me just pull that up. So here we have the picture of equal sets. First, we have our rectangle, which contains the universal set, and then we see only one circle, but that represents actually two sets because A and B are the same set. They are equal to each other. They kind of overlap each other completely. So it's like doing this. Let me just draw here. Let's say this is set A. All right, let's say this is set A, and we want to also represent set B, which are equal to each other. Then if the red one is A, then B would be a circle drawn over the red circle over A. So essentially it looks like one circle, but actually it represents two overlapping circles, completely overlapping circles. Okay, now let's look at overlapping sets. Now although this says overlapping sets, what we will see is they are not completely overlapping sets. That's what equal sets would be. This is kind of partially overlapping sets. So I might as well write here, this is partially overlapping sets. All right. So to pull up the information here, it says two sets A and B with some elements in common. So they are not equal sets, but some of the elements in A also exist in set B, right? So here is our picture with the rectangle representing the universal set, and then we have two circles here, so one for set A, another one for set B, and set A has its own elements, set B has its own elements, but this overlapping section of the circle where we have a red arc as well as the blue arc, that would hold the common elements in both the sets. All right, so this is partially overlapping. It's not completely overlapping. This is partially overlapping where some elements of set A are common with some elements of set B. So the elements outside this overlapping section are the ones which do not exist in the other set. All right, so let's pull up the rest of the information here. So this is the most general form of a Venn diagram. So when you see a picture of a Venn diagram, it'll most likely be shown like this, because there will be two sets where some elements are common and some elements are unique to the sets. But of course, we have seen we can have different views of Venn diagrams as well. Now we'll go through a few cases where we will learn how to represent sets that we had learnt about previously in the general form of the Venn diagram. So we were told here in the last slide that the general form of a set, the diagram of in general form, looks like this. The rectangle holds the universal set, and then we have two circles. We will have two circles and they are partially overlapping each other. So we have set A, let's say the black one is set A and this red circle is set B, and there will be a section of the circles intersecting, but we can represent the different types of sets that we had learned before talking about the general form, called the disjoint sets, the overlapping sets, and also the equal sets. All of those can be represented in the general form of the Venn diagram. So recall what disjoint sets were. Disjoint sets were those where there were no common elements, right? So we talked about disjoint sets. We showed the diagram being like this. There were two circles, but they were not connected in any way, right? So the rectangle had the set of universal elements, and then we saw two circles, but they were not connected. All right, they were not overlapping. They were two separate circles. So that told us that there were no common elements in the two sets. Now over here, so disjoint sets, we do not expect any connection. However, we can represent disjoint sets in this form also, in the general form, by showing them intersecting, but that intersection will really be an empty set. So let's pull up the information here. Set A and B are disjoint. They have no elements in common. And then it goes on to say that we have a picture here, all right, where there is an intersection. We have these overlapping circles dividing the region into three. There's region 1, then the intersecting section is region 2, and then there's a region 3, correct? So now in what happens with disjoint sets is the region 2 is empty because there are no common elements between the two. So we have represented disjoint sets in this form, but we have to mention that this region 2 is an empty set. This part of the will not contain any elements. It'll just be an empty set. All right. Now let's look at case 2, which is on subsets. How do we represent subsets in the general form of a Venn diagram with two overlapping circles, right? So when we talked about subsets, what does subset mean? Subset means that set A, one set, would have all its elements existing in another set, right? So if I pull up the information here, it says when A is a subset of B, and look at the notation for subsets, it's this horizontally placed U with a line underneath it that reads as subset. A is a subset of B. Then every element of set A is also an element of set B. Now they are not necessarily equal sets. Equal sets would mean that they had the same number of elements as well, but in subsets that's not the case. In subsets, B would be a larger set, would have a larger cardinality than A. And when we were discussing this previously, this is how we showed subsets. We had two circles. There was a bigger one, which would be B, and then a smaller one inside, meaning that all the elements of A, so let me just write A for the second, for the inside innermost circle. All right, that means all the elements in A are contained in B, but B had other values as well, which are not a part of A. Correct? This is how we had shown subsets in Venn diagrams, but how do we represent it in the general form with overlapping circles? That's what we want to know. So here is a picture. All right, we have two separate circles here, and then we have a smaller intersection. All right, a smaller intersection. We have the regions, three regions, 1, 2, and 3, 2 being the intersecting region. When A is a subset of B, that means that region 1 would be an empty region. All right, it would be represent an empty region, empty set. So region 1, this one would be represented as an empty set. All the values that are common would be in region 2. All right, and then in region 3 there would be values which are not present in set A. All right, so when we talk about subsets, then the region 1 would be an empty set. So what does it say here? Region 1 is empty when A is a subset of B, but if B were a subset of A, then region 3 would be empty and everything would be between 1 and 2. The intersecting region would have elements of B, all right, and then 1 would have the rest, the remaining of the elements. All right, remainder of the elements. So, but that would be the case if B is a subset of A. So we will have different pictures or different scenarios if A is a subset of B and when B is a subset of A, right? Now it's the same story with equal sets, because if you recall when we were talking about equal sets, we showed the Venn diagram looking like this. There was one circle which was set A and another circle completely overlapping it. It was set B. So A and B represented the same circle. So equal sets mean the sets have the same number of elements and the same elements as well. So how do we represent this equal sets in general form, right? So let's pull up the information. When set A is equal to set B, all elements of set A are elements of set B, and all elements of set B are elements of set A. So what will the Venn diagram look like in this case? So we have our rectangle with two circles divided into three regions. Now we have to determine which regions would be empty and in which region all the values will be. Now because A has the same element as B, region 1, and let me just pull up my pen here. Region 1 would be an empty set. Region 3 would also be an empty set. All the values would be contained in region 2. All right, so all elements would show up in region 2. All right, so regions 1 and 3 would be empty, and region 2 would be the intersecting region, would have the values for A as well as the values for B, because all elements are common here. Now let's look at what's called overlapping sets, but not completely overlapping sets. All right, completely overlapping sets refer to equal sets. Now we will talk about partially overlapping sets. All right, so when sets A and B have elements in common, those elements are in region 2. So we saw that before in our diagrams, all right, for in the general form of the diagram, all the common elements between set A and set B appeared in the intersecting region, correct? Now, for overlapping sets, there are some elements that would be common between the two sets, right? Some elements would be common, but there would be elements in set A which are not present in set B, and there would be some in B which are not present in set A. So in that case, all three regions would have elements. None of them would be an empty region. All right, set A would have some elements, then there would be the common elements in this intersecting region, and then elements of B which are not in elements of A would appear in the third region. All right, so when sets A and B have elements in common, those elements are in region 2, which is the common region. So here we have our diagram, and then it says here elements that belong to set A but not to set B are in region 1. And then elements that belong to set B but not to set A are in region 3. Now, so far we have talked about 3 regions in our Venn diagrams. There is, however, a 4th region which would contain elements which are not a part of set A, neither a part of set B. All right, because recall that set A and set B are essentially subsets of an universal set. So any elements which are outside of set A or outside of set B represent the 4th region. All right, and they are the elements not common to A, nor are they common to B. So in each of the 4 cases, any element belonging to the universal set but not belonging to set A or set B is placed in region 4, in the area outside of the circles, but within the rectangle. Now we will talk about what is called the complement of a set. Now the complement of a set symbolized by A dash, all right, so we use A with a dash on the right hand side of it, is the set of all elements in the universal set that are not in set A, and that's the key word here, that are not in set A. So the elements which do not belong to set A but are in the universe and the universe of values, that would be the complement of set A. All right, so let's look at a diagram here. We have our rectangle containing the set of universal elements, and then we have a circle which represents the elements in set A. So when we talk about A dash, then we are looking at all the values outside of set A, the elements that are not in set A. So those elements would exist outside this circle but within the rectangle. So let's look at an example now of identifying the complement of a set. So example 1 is on a set and its complement. So given a universal set of values and A, which is a subset of the universe, we have to answer the question what the complement of A would be. So let's try to do that before we pull up the solutions over here, and I can explain in the process. So U represents the elements A, B, C, D, E, F, G, and the subset A only has the elements A, C, E. So what would A dash, which represents the complement, what would A dash be? All right, the complement of A, B. So the complement would contain all the values of the set which are not in A. So we have to see which values in the universal set do not belong in set A. So this is A, this is also exists in set A. So this is not a complement. All right, this element should not go to the complement. The complement will only have elements from the universal set which do not belong in set A. All right, so does B belong in A? No. So B would be a part of the complement set. So we have B, and then we see there's a C, but C also belongs in A, so we cannot put that as a complement. So let's go to the next one. D in the universal set does not belong in A, so yes, this is the one that. So this one, what else did we pick before B? So now we have D. E belongs in set A, so we cannot include that in the complement. And then F, this one, and G, right? So F comma G. So the complement of set A dash, will contain these elements B, D, F, G. All right, from the universal set which are not in set A. So let's look at the solutions here. It says determine A dash and illustrate the relationship among sets U, A, and A dash in a Venn diagram. So they're going to bring up the solution in the next slide, but let me do the Venn diagram over here, and then we can go back and check in the next slide whether the answer, their solution matches with ours. So here we have the universal set, and the universal set has a subset A, and the elements of subset A are A, C, and E, correct? Those are the elements of set A. The elements not in set A would be A dash, and what elements would be in that area outside of set A are all these values. So I'm going to write B, D, F, and G. All right. So this is how we would be representing this particular set uh, in a Venn diagram. All right. So here's the solution. All of the elements in U that are not in set A are B, D, F, G. Those are the exact values we got in the complementary set. A dash equals B, D, F, G. And look, they have drawn it in a Venn diagram with U being within the rectangle. So B, D, F, G are represented as the complement of set A, which contains the elements A, C, and E, right? So set A had the elements A, C, E, and all the elements that do not belong to set A, but were a part of the universal set are written outside, but within the rectangle, outside the circle, but within the rectangle. And you have to put down the elements here, B, D, F, G. Now let's talk a little more about the intersection of two sets, right? So the intersection of sets A and B symbolized by A, and then this downturned U represents intersection, is the set containing all the elements that are common to both set A and set B. All right, so this is the notation for representing intersection. We can either write it as A and then an inverted U and then B. So that tells us that we are talking about the elements that are common to both A and B. Or we can write the same thing in this notation as well, A and B. All right, it means the intersection. That means elements common to A and B as well as B. All right, so the intersection of sets A and B symbolized A intersection B is the set containing all the elements that are common to both set A and set B. So here's our diagram over here. We've seen this before. We have the rectangle with the set of universal elements, all the elements in the universe, and then two intersecting circles, partially intersecting circles, and all the intersection would be, the common elements between A and B would be contained in region 2, which is the intersecting region, right? So region 2 represents the intersection. Now we will go through an exercise of finding the intersection between two sets given a set of elements for the universe, a subset of the universe named A, a subset of the universe which is named B, and C, which represents an empty set. All right, so let's look at the values in the set of universe here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? All natural numbers up to 10. A contains the value 1, 2, 3, and 8. B contains the values 1, 3, 6, 7, 8. These are elements in B, and C is a null or empty set. The first part of the question says find A intersection B. So the elements that are common to both A and B. So we look at the two sets here, all right, set A and set B, and figure out which are the common elements, and we are going to list them here in roster form. So we see that 1 is common, 2 is not common, but 3 is common, 6 is not common, 7 is not common, 8 is common to both the sets. So the way we are going to write this would be 1, 3, 8. So let's write it here for A, the intersection here. A intersection B would contain these values 1, 3, and 8. All right, how about A intersection C? This would be, but C is an empty set, so we would have to list, there's nothing common here, right? So we'll just leave it like that. It would be, we would just keep it as an empty set, all right? And then we have A complement intersection B. All right, now what is A complement? We first have to figure out what A complement is. So A complement would be all the elements which are not, all the elements in the U, in the set of universe, which are not in set A, correct? So 1 is there, 2 is there, and 3 is there, but 4, 5, 6, 7, 8 is there, right? So I'm going to mark these values before I start writing them. 4, 5, 6, 7, 9, and 10 are A dash, A complement. So I'm going to list those first. 4, 5, 6, 7, 9, and 10, correct? And then I'm going to look at this set and set B, and set B to find the intersection. So what do we have common here? So 6 and 6, these are common. These 6 is a common value between, common element between the two sets. 7 is also common, so we take that. 8 is not common, right? So it's essentially 6 and 7. So the set is going to be 6, comma 7. All right, and then A intersection B, and then we have the complement. All right, A intersection B and complement. Now in this case, A intersection B is surrounded with brackets, so we have to first figure out what A intersection B is, and then we have to find its complement from the universe. All right, so we already worked out A intersection B in part A, so you do not need to work it out again. Just take these values. So A intersection B is 1, 3, 8, right? Now we have to find its its complement. All right, A intersection B, the complement. That means the values in the set of universe which do not belong to A intersection B set, this set. So 1, 3, and 8 are A intersection B elements, so we have to leave out those values here. I'm going to briefly erase these because otherwise it's going to cause some confusion. So, and then let's cross out the values which are not 1, 3, 8. So we will choose, let's use a different color. 2, 3, well, 3 is common, we cannot choose 3, 4, 5, 6, 7, 9, and 10, right? So these are the values which would be A intersection B and then its complement. So I'm going to write these in a set: 2, 4, 5, 6, 7, 9, and 10. All right, so this is how we are going to perform operations for the intersection, different forms of intersections. Now let's go over the solutions and see whether they match with the answers that we came up with. So the first one was to find A intersection B. So they've listed the elements in set A, 1, 2, 3, 8, and then after the intersection symbol, they've listed the elements from set B, 1, 3, 6, 7, 8. So remember, intersection means the common elements in both sets. So if that were the case, then we should come up with all the common elements. So let's circle all the common elements. 1 and 2 is not common to both, but 3. All right, so we'll have to pick 3, and then the last one is 8, correct? So the answer would be 1, 3, and 8. So let's see if that's what they have come up with. So the elements common to both set A and set B are 1, 3, and 8, and that's what we came up with as well. Now part B was to find the intersection between set A and set C. Set C was a null set, empty set. So they've listed the elements in set A, 1, 2, 3, 8, and then the intersection symbol followed by set C, which is an empty set. So there's nothing common here, right? So there's no there are no elements that are common, and that's what we should be writing for our solution, that there are no elements common to both sets A and C. Now the third part had to do with the complement of A. So it was find A complement and then the intersection with B. So we are finding the intersection between A complement and B, not A intersection B, but A dash or A complement intersection B. So the first step would be to determine A complement. That means we have to find values from the universal set which are not 1, 2, 3, 8. That means the elements of A. And when we do that, all right, we come up with the elements in A complement. Those would be 4, 5, 6, 7, 9, and 8. All right, we list everything except 1, 2, 3, and 8. All right, so once we have A complement, we will list the elements of B, set B, and find the common elements and list them. All right. So A complement intersection B would be 4, 5, 6, 7, 9, 10. And then intersection, we list the elements of B. And then we find the common, we pick the common ones. So the common ones are which? There's no 4, there's no 5. So 6, right? 6 is common. Let's pick that. So 6, and then 7 is common. 7, right? 9 is not common. 10 is not common on this side. 3, 1 is not common. 3 is not common. 8 is not common. So the only elements that are common are 6 and 7 would be our answer, right, for this one. And finally, we had one which said A intersection B and the complement of that. So in other words, the complement of A intersection B. So first we have to determine what A intersection B is. So A intersection B are the elements common to A and B. So what we had already found that out before. So that list of elements were, all right, so A intersection B were which values here? 1, 3, and 8, correct? 1, 3, and 8. So once we have A intersection B, we have to use those elements and compare them or look at the set of universe values and pick the values which are not 1, 3, and 8 from the set of universe. All right, so that's what they have done here. So A intersection B is 1, 3, 8, exactly what we found. And now they are going to go to the set of universal elements and pick all the values which are not 1, 3, 8. So complement also reads as not A intersection B. All right, it can also read it as not A intersection B. So not 1, 3, 8. So we will be picking all the values which are not 1, 3, 8 and come up with this list of values. All right, 2, 2, 4, 5, 6, 7, and then 9 and 10. So these are the ones which we cannot pick from the set of universal values because those are A intersection B. All right. So this is how we work through these problems. We'll now look at another operation or another relationship between two sets, and that's called the union. So far we were dealing with intersections, which is the common elements between two sets. All right, intersections only refer to the common elements between two sets. In unions, first of all, we denote unions in this form: A being one set, and then the letter U, which represents union, and then the other set B. A union B, what this does is it combines the elements of set A with the elements of set B. And if there are any common elements, those are stated once. All right, you don't duplicate them. So A union B is a combination of all the elements in set A and the elements in set B, and the common elements are stated once. All right, so let's pull up the information here. The union of sets A and B, symbolized A union B, is the set containing all the elements that are members of set A or of set B or of both sets. That means the common elements as well need to be stated, but you state them only once. Now, here's a picture, a Venn diagram in general form, and in the union, what happens is we see three regions. That's always there in the general form, with region 2 being the intersection, the common elements. This region will always carry the common elements between A and B. So regions 1, 2, and 3 represent the union. So when you have to write out the union of two sets, you have to state whatever is in region 1, in region 2, as well as region 3. Let's work on some examples of the union of sets. So they've given here the universal set, which is a set of natural numbers from 1 through 10, and then set A, which is a subset of the universal set, and set A has elements 1, 2, 4, and 6. B is also a subset of the universal set, but it has elements 1, 3, 6, 7, 9, and C is an empty set. All right. So based on this information, we are first asked to find A union B. So we have to combine the elements of A with the elements of B, and then we have A union C, A complement union B, and then A union B, the whole set complemented. All right, so we will first work through these problems ourselves, and then we will go to the solutions and see if the answers match. All right, so let's work on the first one, which is A union B. So what I'm going to do is I'm going to list all the elements of A, which are 1, 2, 4, and 6. So let's do this here. All right, so A union, so the elements of B are 1, 3, 6, 7, and 9. All right, so next to the elements of A, I have used the union symbol, and then I wrote out the elements of B, 1, 3, 6, 7, 9, and now we have to write the result of the union of both the sets. So remember, we have to include all the elements from A as well as the elements of B in one set. And if there are any common elements, we have to include them once. We don't have to repeat them. So let's look at the elements. Let's pick the element. So this will be equal to, all right, and I'm going to work below here. So there's 1, correct? 1 is a common element, so we are going to write that once. And then there's a 2 in A, we should include that. And then there's a 3 in B. There's a 4 in A. And then there's 6 that occurs in both sets. It's a common element, so write that just once. 6. And then 7 and 9 from set B. 7 and 9 from set B. So here I'm going to write 1, 2, 3, 3, 4. Remember to include your commas. 4, 6, 7, 9. All right, so that's A union B, the result of A union B. Now we have A union C, correct? C is an empty element. So what we are doing is I'm going to erase the writing from the previous exercise, from the previous part that we worked out. So let's erase that. So this time A union C would be the elements of A combined with the empty set. So empty set basically means nothing. So it's going to be 1, 2, 4, and 6. All right, 1, 2, 4, and 6. Now, if you want, you can just write a null, all right, to indicate that you have combined the empty set in here. Otherwise, we can just write it as 1, 2, 4, and 6. This is good enough. All right, so the third one, part C, says a complement, just a second here, let me pull out the pointer, a complement union B. All right, so what this means is we have to first create a set which is a complement of set A, and then we have to do the union of that with set B. All right, so we have to perform this over multiple steps. So let's just write this out. The first step, we have A given to us, but we first have to find what A complement is. All right, complement of A is the same as saying not A. So we have to go to our universal set, all right, the set of natural numbers, the universal set, and then from there we have to pick the values which are not in set A. So what I'm going to do is I'm going to cross out the values in the universal set which belong in set A, and then it'll be easier for us to pick out the values of not A. So we cancel 1, we cancel 2 because those are in set A. We cancel 4, we cancel 6, and I'm going to pick everything else from set U. All right, so not A, or the complement of A, this set is now going to look as 3, 5, 7, 8, 9, and 10. All right, and now that we have A complement or not A, we are going to do its union with B, correct? So let's write out the elements in B: 1, 3, 6, 7, and 9. And now we are going to create a set of union between the two. So again, all the values have to be listed from not A set, from this set, the complement of A set, as well as those in B. All right, so we start with 1, lowest value first. 3 occurs twice, correct? 3 occurs twice, but we write it once. 3 is a common element between both the sets. Then we have the 5, then 6, 7 occurs in both the sets, but we list that once. And then we have 8, 9, and 10. All right, so A complement union B would be this set here. 1, 3, 5, 6, 7, 8, 9, and 10. All right, the next one, the last one here is A union B and then the complement of A union B. All right, so first we have to find out what A union B is. So again, I'm going to erase our previous work. Let's erase our previous work and start fresh. All right, so A union B would be all these values, right? We already worked through that in part A, 1, 2, 3, 4, 6, 7, 9. So let's list that. All right, it's 1, 2, 3, 4, 6, 7, 9. All right, now we have to find a union B complement. All right, the complement of A union B. So now I'm going to go to my universal set, all right, to U. And first I'm going to cross out the values, all these values that exist in A union B, and then I'm going to pick the ones which remain, all right, because A union B complement is the same as not A union B. So we have to pick the values from the universal set which are not in A union B. So to make things easy, let's just cross out the numbers which exist in A union B. 1, 2, 3 occur, 4 occurs, 6 occurs, 7, and then 9. So what are we left with? We are left with 5, 8, and 10, correct? So let's write that. A union B complement, or the complement of A union B, would be 5, 8, and 10. All right, so the final result here is 5, 8, and 10. All right. So now let's look at the solutions they have given us and see if they match with what we got when we worked them out. So over here for the first one, it was just A union B. So they listed all the elements of A with all the elements in set B as well, and they are taking the union of both the sets. And their result is 1, 2, 3, 4, 6, 7, 9. So so they list the common ones only once, and this is the same as what we got when we worked it out in the previous slide, right? The next one was combining the elements of A with C. So it was A union C. Again, they listed the elements of set A first, and then the union symbol followed by the elements of C, which was an empty set. And the result is 1, 2, 4, 6. That means all the elements in set A, correct? So the final result is that A union C, when C is an empty set, will be just the set A, all right? Now for part C of the problem, which was A complement union of B, we first had to determine what not A was. Again, to remind you, A complement or the complement of A is the same as saying not A. That means we have to pick the elements from the universal set, the elements which are not in set A, correct? So let's see what values they came up with under A not or A complement. So here are the values for A complement: 3, 5, 7, 8, 9, 10. We have to make sure that the elements in A are not included in A naught. So 1, 2, 4, and 6, none of them occur here. So 3, 5, 7, 8, 9, and 10 are in the set of A naught. And then we have to combine that with B, correct? So A naught union B, they have listed A naught, all the elements in A naught, and then the union with all the elements in B for a result of 1, 3, 5, 6, 7, 8, 9, 10, right? 1, and then 3, then 5, then 6, 7, 8, 9, and 10. And finally, the last part was to find the union of A and B naught, or the complement of A union B, right? So for that, we first had to find what A union B was, and then we would take the complement of that. So let's see what they came up with. A union B. A union B was the first set we had to work on. So 1, 2, 3, 4, 6, 7, 9, those are A union B. And then we have to go to find the complement of that, we have to go to the universal set and pick the elements which are not in this set. All right? So let's see what they come up with. A union B naught would be 1, 2, 3, 4, 6, 7, 9 naught. So just make sure that you understand what we are doing here. All right? The final set, the final answer is not this. We still have to find the elements which are not 1, 2, 3, 4, 6, 7, 9 in the universal set. All right, so there's another step to it. 5, 8, and 10 are what we come up with. So in other words, what we did was we cancelled out all the elements in AUB or A union B, which were 1, 2, 3, 4, and then 6, 7, and 9, and then pick the remaining ones, which were 5, 8, and 10. All right, so A union B naught, or the complement of A union B, is 5, 8, and 10, this set here. So now we are going to discuss what these two words and or mean in context of set theories. And or essentially is another word used to describe intersection and union respectively. So and goes with intersection. All right, remember the symbol for intersection was this downturned U, correct? This downturned U. And for or, it was a U symbol, correct? So let's see what this has to say. The word and is generally interpreted to mean intersection. That means it will refer to the common elements between the two sets. Now, in set notation, this is how it's going to read. A intersection B would be all x values such that, remember this vertical line reads as such that, let me write that here. This reads as such that, so x is an element such that x is a member of the set A and x is a member of B. So again, intersection means the common elements, the elements that belong in set A as well as in set B. So in the set notation, this is how it reads: x such that x belongs to A and it also belongs, x also belongs to B. Now let's look at what the or word interprets to be. All right. So the word or is generally interpreted to mean union. What is the symbol to denote or union is this U symbol, correct? So in set notation, this is what it's going to read like. A union B is equal to x such that, again, vertical line means such that x belongs to A or x belongs to B. All right, so that means you have to include elements from A as well as the elements from B. You cannot exclude any of the elements. All right. So now we are going to see if there's a relationship between the number of elements in A union B with the number of elements in set A, number of elements in set B, and the number of common elements between A and B. All right. So recall that the set A union B is a combination of set A, or rather is a combination of the elements in set A with the elements in set B, with the common elements represented only once, right? The common elements were in set A as well as in set B, but we did not double count them. We included them only once. So when we want to when we want to determine the number of elements in the union of set A and B, it's going to look like this. N of A union B will be equal to, you take the size or take the number of elements in set A. To it you add the number of elements in set B, but since we included the common elements only once, we have to take out one set of common elements between A and B. So it's minus n combination, sorry, n uh, n of A intersection B. All right. So if we do not subtract one set of common elements, then we will end up with double counting. If we just take n of A and n of B, and we do not subtract the one set of common elements, then we'll end up with a different value for n of A union B. All right, so let's see what it says here. It says to find the number of elements in the union of two sets A and B, we add the number of elements in set A and set B, and then subtract the number of elements common to both the sets. All right. So here is the equation to find the cardinality of A union B. And it's the same equation that we just came up with in the previous slide. N of A, that means the cardinal of A, plus the cardinal of B, minus the cardinal of A intersection of B. In other words, the number of elements in A plus the number of elements in B minus the number of common elements between A and B would be the number of elements in A union B. So let's look at this example here. It's about how many visitors speak Spanish or French. The results of a survey of visitors at the Grand Canyon showed that 25 speak Spanish, 14 speak French, and 4 speak both Spanish and French. How many speak Spanish or French? All right, so let's just list again. We are just dealing with the cardinal numbers here. We do not need to create a roster form of different sets, but there are two sets that we are dealing with. One is the set of Spanish speakers. All right, so Spanish speakers is, let's call that S. So Spanish speakers, set of Spanish speakers is one set. The other set is the set of French speakers. So let's write this as F refers to the set of French speakers, and N of S is how much? N of S is 25. N of F, so N of F is 14, and 4 speak both Spanish and French, so that's the commonality. So we have to write this as N of S intersection F, or you can write it as N of S and F. Remember, and the word and also denotes intersection. So N of S and F would are the common speakers who speak both French and Spanish. So they want to know how many speak Spanish or French. All right, so that would be denoted as N of S, or which we can write as this U, S, U, F. All right, we could have written it as S or F as well, is equal to N of S plus N of F, right? Again, let's make this capital just the way we represented it earlier, minus N of S intersection F. All right, so N of S is 25 plus 14 minus, this was 4, correct? Minus 4, which is 25 plus 14 is 39. 39 minus 4 is 35, right? So N of S union F, so that means the number of elements in Spanish or French would be 35. So how many speak Spanish or French? 35 speak Spanish or French. So let's review the problem here and go through what they have done to work this problem out. So set A is visitors who speak Spanish. That's how we designated it, and we just named it as set S instead of set A. And then set B is visitors who speak French. We did the same thing, except we denoted the French speakers as set F, correct? Set F. And then we need to determine A union B, correct? So N of A union B is equal to n of A, number of elements in A, plus number of elements in B, minus the number of common elements between A and B. So we have 25 plus 14 minus 4 is what we did 2 for an answer of 35, right? Now let's look at a particular operation called difference of two sets. All right. So the difference of two sets is denoted as A minus B. All right. So let's pull up what we have here. The difference of two sets A and B is symbolized as A minus B, is the set of elements that belong to set A but not to set B. All right. So here we have a Venn diagram showing us what A minus B would look like. So in the answer for the difference of two sets, we only include the elements in set A which do not exist in set B. All right. The, the result would be only the elements in set A which do not belong in set B, and we even take out the ones which are the common ones because they also belong to B, correct? So even the common ones are subtracted here. So region 1 is the solution. So all elements in region 1, and that represents the difference of the two sets. So essentially you are eliminating all elements in region 2 as well as region 3. So let's look at how the difference of two sets would be represented in set builder notation. So it says here, using set builder notation, the difference between two sets A and B is indicated by A minus B is equal to, so the set which is composed of A minus B would contain elements X such that X belongs to A. That means X is a member of A. Remember this this notation here, symbol here, which looks like an E, means member of. So X is a member of A and X is not a member of B. All right, so this is how it is expressed in set builder notation. Let's work through an example on the difference of two sets. So we have been given four sets here. One is the universal set, which contains elements from A through K, the letters A through K. And then set A, which is a subset of the universal set, contains these letters, these elements as letters B, D, E, F, G, and H. B, set B, which is also a subset of U, contains the letters A, B, D, H, and I. And then we have C, which contain the letters as elements B, E, and G. So the first question says, find the difference between set A and set B, or A minus B. So again, I'm going to work these problems here first, and then we are going to go and check the solutions to see if our answers match or not. So A minus B, remember what difference means? It means include all elements which are in set A but not in B. All right, so here we have the list of elements in set A, B, D, E, F, G, H, and from that we have to subtract all the elements which are in set B. So I'm going to list the elements here from set B, which are A, B, D, H, and I, correct? So let's look at which elements are in B. We are going to cross those out from A. So we have to cross out the we have to cross out the common elements as well, correct? So the final set would be here. A is not there in uh, set A, so we are good. Then we have a B in set B, so we have to cross this out. So that cannot be a part of the A minus B set. How about D? D is also there in B, so let's cross that out. E is fine. We can write that. F is fine, right? There's no F. Yeah, there's no F in B, right? In set B, so we are good there. There's no D. We can include the G, and H again is in set B, so we cannot include that. All right. So E, F, G is the final solution, right? E, F, G. So A minus B is going to be the set E, F, and G. How about A minus C? To work on A minus C, let me just erase and make space to work that problem. Here, I'm going to remove the elements of set B and put here the elements from set C, B, E, and G, correct? So now let's cross out the elements which are in set C. All right, so from set A, we are going to remove the elements that are in set C. All right, so B is there in set C, so let's eliminate that from set A. E is also there in set C, so we are going to eliminate that as well. And then G is also there in set C, so we are going to eliminate that as well. So what are we left with? So A minus C will be a set including D, F, and H, these three elements only. So it's going to be a set containing D, F, and H. All right. The next one is A complement minus B. So again, this time we have to first figure out what A complement is or not A is, and then we have to subtract the elements of B from A naught. So let's again remove or make space to work on that part C of the problem. So first we have to figure out what A naught is, all right? So we go to the universal set and cross out. I'm going to cross out all the elements of set B from the universal set, all right? So B is 1, so let's remove that B. Then we have a D we need to remove. Then there's an E. Let's remove that. There's an F. Let's remove that. There's a G. Remove that. And there's an H. So we have to remove that. So what are we left with for A naught? It's going to be A, C, I, J, and K. All right. And from here now, we have to subtract B, the elements of B. All right. So what do we have as elements of B? A, B, D, H, I, correct? So I have to now cross out the common elements between A naught and B. So we have A is a common element, so I'm going to cross that out. C is not a common element, so I'm going to keep that. So is B, right? There's no B in A, so we are good there. I is a common element, so I need to cross that out from A naught. And then J and K are not common elements. So our final answer of A naught minus B is going to be C and J. We only look at the elements remaining in A naught, all right? This first letter, A naught. So C, comma, J, comma, K is our final answer. So let's write that. It's C, comma, J, comma, K. All right? And the final one is A minus C naught. So this time we have to figure out what C naught is. The A remains as it is. This set here will not change. We don't have to worry about finding the complement of A. This time we have to figure out the complement of C instead. All right. So again, let me make space here and remove all the markings on the set so there's no confusion. So just give me a couple of seconds here. All right. So A minus C naught, we have to figure out from the universal set which ones we should remove to come up with the elements of C naught. All right. So we have to remove this B from the universal set. We have to remove the E from the universal set, and we have to remove the G from the universal set. So C naught is going to be all these values: A, C, D, F, H, I, J, and K. All right. And the question is A minus C naught. So let's list the values of A, which are these elements B, D, E, F, G, H. So when we subtract these two, A minus C naught, we have to again remove the common elements from A, all right, from A. So A is not common, so let's see what is common. B is fine, right? This is good. D is common. We have to remove that. Not from here, though. Just a second. Then we have E is not common. F is common, right? So let's remove that. Not from here. I don't know why I keep doing that, but it has to go from the top set, all right, A. So F, let's remove that. And then G is not common, but H is common, so we are going to remove that. All right. So what is our final answer for A minus C naught? Are all the remaining ones, B, E, and G. All right. So we're going to list out those, B, E, and G, and then write them here. B, G, or B, E, and G. B, E, and G. All right, which is the same as what C was. So when we did A minus C naught, we ended up with C, the same set as C. All right, so now let's go and check the solutions to see if we did this correct. Now let's go over the solutions and see if they match with the answers that we got, right? So here we have the sets given to us, and we were supposed to find A minus B for the first part, and we were given the universal set, set A, set B, and set C, and we were supposed to find the difference between A minus B. So the difference would be the values in set A which are not in set B. All right, so A minus B is the set of elements that are in set A but not in set B. All right, so what we are going to do is we are going to go through these two sets, A and B, and from A, we are going to cross out the elements that exist in set B, right? So that's what we had done. So let's go through the set B. I'm looking at set A right now. The first element is a B. Now B exists in set B, so I'm going to cross out the B from set A. Then D, right, D in set A also exists in set B, so we are going to cross that out. All right, that will not be in the new set of difference. Then E does not exist in set B, so we are good with that. F does not exist in set B. G does not exist in set B. H exists in set B, so we are going to cross that out from set A. And whatever we are left with will be the elements of this new set A minus B. So E, F, G represents the difference between set A and set B. All right, and that's exactly the answer that we also got when we worked through this in the previous slide. Now let's go through the second part of the problem, which I believe was A minus C. All right, so we have to determine what the set A minus C would look like. Again, these four sets remain the same. The elements in these four sets remain the same, but this time we are comparing A and C. So I'm going to go through the list of A, the set A, and then I'm going to eliminate from A the elements that exist in set C. All right, and then the remaining ones, after I cross out the elements in A which exist in C, whatever remains will be a part of set A minus C. All right, so let's go step by step. First, we have a B in A, and that B also exists in C, so we have to cross out the B. All right, we have to cross this out. The next one is a D. D does not exist in set C, so we are good with that. E exists in set C, so let's cross out the E from A. All right, I'm going to cross that out. And then we have an F. F does not exist in C, so we are good. G exists in set C, so we have to cross this G out. And finally, there is the H, and H does not exist in C, so we are good. Now we have to pick up the remaining elements in set A and put them together in a set. So D, F, H would be the elements in the set A minus C. So A minus C is the set of elements that are in set A but not in set C. So A minus C is DFH. All right, DFH is the answer we got to when we worked this out. Now the next part of the problem was to find A naught minus C. All right, sorry, A naught minus B it was. So we have the complement of A minus B. So we first have to determine what the complement of A is, and then from there we have to subtract the elements in B. All right, so the first step is to determine A naught, or the complement of A. So A naught was ACIJK. Again, recall that to find A naught, or the complement of A, we have to look at the universal set, and from there we have to eliminate the elements that exist in set A, because we are picking up the ones which do not belong in set A right, from this universal set. So let's do that. Let's go through that exercise one more time. We cancel out the B because that's in set A. C is fine. We cancel out the D. It's not in set A. It is in, sorry, let me do this again. Excuse me. C, D, yes, D is here, right? So we cancel out the D. All right, D is common. For a second, I got a little bit confused there. And then E exists in A, so we'll cross that out. F exists, so we cross that out. G exists as well in A, we cross that out. And H exists also. We cross that out, and we are left with A, C, I, J, K, and that's what A naught is, A, C, I, J, K. And then from there, we have to subtract B. That means the elements in B. So let's write that. It's minus, minus A, B, D, H, and I. So we have to eliminate the elements in set B from the elements in A naught. So we eliminate the A. There's no C. We have to eliminate the I, all right? And I think we are good with the rest. So the final answers should be C, J, K. So let's see what the final answer is, all right? So final answer, A naught minus B, or the complement of A minus B, is equal to CJK. And that's exactly what we got when we worked this through. Let's look at the last solution that we worked on. So this one was A minus C naught. So, or A minus the complement of C. So this time A remains the same, but we have to first find what C naught is. So again, we go back to the universal set. From there, we cross out. I'm going to cross out the elements that are in C and pick out the remaining ones. All right, so let's go through that exercise. I'm going to cross out the B because that exists in C. I'm going to cross out the E and the G, and so C naught will be, or the complement of C will comprise of these elements A, C, D, F, H, I, J, and K. All right, A, C, D, F, H, I, J, and K. So that's going to be our C naught. So what are we subtracting here from? We are subtracting from A, which is B, D, E, F, G, H. Let me write that here. B, D, E, F, G, H minus A, C, D, F, H, I, J, K. So which are the elements we should be removing from A? All right, so here, B does not exist in C naught. We are good there. D exists in this set. So I'm going to remove D. Is there an E? No. Is there an F? Yes. Is there a G? No. There's an H. All right. So the list should consist of A minus C naught. That list is going to consist of the elements B, E, and G. So let's see what we have here. C naught is A, C, D, F, H, I, J, K, exactly what we got, right, when we determined C naught. And then A minus C naught will therefore be B, E, and G. All right. Now there's one more operation that we need to know about. that is done on sets is called the Cartesian product. Now, the Cartesian product will have the end result of having pairs of elements. So we will have two sets A and B. All right, so there'll be set A and set B, and we are going to pair up the values, the elements in A with the elements in B in a certain way. So that's what we are going to learn just now. That's what is going to be performed using the operation Cartesian product. So here it says the Cartesian product of set A and set B, symbolized as A times B and read as A cross B actually. So even though we use the multiplication sign, the X multiplication sign, but we read it because it's a part of set theory, we read it as A cross B is the set of all possible ordered pairs of the form A comma B, where A belongs to set A and B belongs to set B. So we are going to end up with a pair of values, all right? One value will come from set A, the other value B will come from set B. So we'll go through some examples and we will learn the process of figuring out of working through a Cartesian product on set theory. So here's the process of coming up with the ordered pairs. It says select the first element of set A and form an ordered pair with each element of set B. So here are the key words. Select the first element of set A and we are going to combine it with each element of set B. All right. So to give you a quick example, let's say set A. All right, set A has these elements A, B, and C, and set B has the elements 1, 2, 3, and 4. All right, so to create a Cartesian product and the ordered pairs, the result from the Cartesian product, you're going to first take A, all right, from set A and pair it with every element. You have to pair it with every element in set B. So this is how it's going to be A, all right, A1, A2, A3, A4. So our pairs are going to be A comma 1, A comma 2, A comma 3, A comma 4. All right, and then once we are done with combining the A's with all elements in B, we are going to move to B in set A and then combine it with, let's pull up another color here, B1, B2, B3, and B4. All right, so we are going to end up with B comma 1, B comma 2, B comma 3, B comma 4, and then we are going to move to C once we are done working with combining the B with all the elements in set B. We are going to move on to C and then go C comma 1, C comma 2, C comma 3, C comma 4. All right, so it's going to be C comma 1, C comma 2, C comma 3, and C comma 4. So that's the process, but let's read through the rest of what they have up here. Then it says select the first element of set A and form an ordered pair with each element in set B, and we list them. Then select the second element of set A, second element, and form an ordered pair with each element of set B. That's what we did. And then continue this manner in this manner until you have used each element in set A. So that's the exact process that we went through and created the Cartesian product of A and B. All right. So here's an example. It says given A equals orange, banana, and apple, and B equals 1, 2, determine the following A cross B. And then another one will be B cross A, then A cross A, and B cross B. All right. So we are going to go through this exercise, A cross B first, and list the ordered pairs. So recall what we have to do is we have to take each element in A and combine it with all elements in set B. Right then, and we are going to move through all the elements in set A in this way. So we'll start with orange. All right, so we are trying to work on A cross B. So orange, comma, orange has to be combined with, actually let's write the uh, sets out here. All right, A equals orange, banana, and apple. And B is just 1, 2, right? 1, 2. So when it's A cross B, then this is how we are moving along. We have to first combine orange with 1 and then orange with 2. So our ordered pair is going to look like orange, 1, and then orange, 2, 2, right? And then we move on to banana and have another pair with bananas. Banana, 1, banana, 2. Banana, 2. All right. Next we have apple. So we are going to get another ordered pair with apple, 1, and then apple, 2, 2. All right. So how many pairs did we get here? We got 1, 2, 3, 4, 5, 6. All right. So A cross B would be 6 pairs where we combined each element of A with all elements in B. All right. The next one here says B cross A. Now this time B is going to be on top. So it's going to be B equals 1, 2, and A is going to be orange, banana and apple, banana and apple, right? So now we are combining 1 with orange, banana, apple. So 1 orange, 1 banana, 1 apple, and then 2 orange, 2 banana, and 2 apple. All right, so let's list that. So for B cross A, we would have 1, 1 orange, 1 banana, 1 apple, and then 2 orange, 2 banana. Sorry, these should be braces. And what's it? 2, sorry, 2 apple, right? 2 apple. All right. The next one is A cross A. Now I have to erase some of this writing here, otherwise it's becoming too cluttered and very difficult to read. So let's erase everything and start again. All right, so A cross A means we are combining the elements of A with the elements of A. So A is orange, banana, apple. And let's write again below it, set A, orange, banana, and apple. All right, so what are the ordered pairs we are going to get? Orange, comma, orange, orange, right? Orange, comma, orange, orange, comma, banana, orange, comma, apple. So orange, comma, banana, orange, comma, apple. Then we have banana, comma, orange, banana, comma, orange, banana, comma, banana, and banana, comma, apple. All right, and then finally, so what we just did was banana, orange, banana, banana, and banana, apple. And then finally, we'll have to work with apple. So apple, orange, apple, banana, apple, apple. So we'll end up with apple, orange, apple, banana, and apple, apple. All right, so that would be the Cartesian product of A cross A and A, the Cartesian product of A. And finally, we have B cross B, where we work with 1, comma 2. So B equals 1, the set 1, comma 2. And let's write another B because we are essentially finding the Cartesian product of the set B with B. So what are our combinations going to be? The ordered pairs. 1, all right, so 1, comma 1, 1, comma 2, 1, comma 1, 1, comma 2, and then 2, comma 1, 2, comma 1, and 2, comma 2. So let's list that 2, comma 1, and 2, comma 2. So that's the process we are going to use when we work on Cartesian product of two sets. But let's go through the solutions and see if they worked it the same way as we have. All right. We are now going to pull up the solutions and check if they agree with what we came up with when we worked on this problem. All right. So here the set A has orange, banana, and apple as their elements, and B has 1, comma 2. We are supposed to come up with the Cartesian product of these two sets. So recall what we need to do. We have to take each element from A and combine each of these with all the elements in B. All right, so we should have orange 1, orange 2. Once we are done with uh, pairing them up with all the elements in B, we go to the next element in A and repeat the process. So we'll get banana 1, banana 2, and then apple 1, apple 2. So that's what they have here. So A cross B has these pairs in their sets, or orange 1, orange comma 2, banana comma 1, banana comma 2, apple comma 1, and apple 2. All right. Now for the question, which is B cross A, what we do is we take each element in B and pair it up with all the elements in A. It's the reverse that we are doing here because it's B cross A. B is first. So we will take each element from B and combine it with all the elements in A, and thus we'll have 1 comma orange, 1 comma banana, 1 comma apple. All right, 1 orange, 1 comma banana, 1 comma apple. And then we start with 2 from set B and pair that up with all the elements in A. So 2 comma orange, 2 comma banana, and 2 comma apple. To create a Cartesian product of a set with itself, as in this case A cross A, what we are doing is we are pairing the elements of the same set with each other. All right, so we have orange, banana, and apple. So we are going to pair them up with, so it's better to actually write it like this. So I'm going to, for the time being, cross the B out and write A equals orange, because that way it'll be easier to see what we are supposed to do. All right, orange, banana, apple. So the same set we write below, and then we start pairing. So orange, 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 banana, orange, apple. And then banana, orange, banana, 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 apple, apple, orange, apple, banana, apple, apple. And that's exactly what we have here. A cross A is orange, 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 banana, orange, apple. Then we are done with all the pairing everything with orange from the top row of set A. And then, but we start the same process with banana, banana, orange, banana, banana. So that's what we have here, banana, orange, banana, 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 apple. And then we start the process with apple. All right. So if it is pairing with the elements of the same set, then just write the set again below. It'll be easier for you to pair the elements. All right. So let's look at the solution when we pair the elements of B with the elements of itself. All right. So the Cartesian product for B cross B would be pairing the elements of the set with its own elements. All right, with its own elements. So let's follow the same process, but first I'm going to cross out the top row, the set A, so it doesn't confuse us. And below, where they have given us set B, I'm going to write one more time the elements of set B. So B equals 1 comma 2. So I'm going to take the first element from the top row and pair them, or pair it with the elements of set B in the bottom row. So 1 comma 1, 1 comma 2. So that's why we have 1 comma 1, 1 comma 2. And then once that is complete, we take the second element from the top row and pair it with the elements in the bottom row. So 2 comma 1, 2 comma 2. All right, and that's exactly what they have here.